an op-amp has 5 pins. So there's a positive power supply, a negative power supply, so we have 2 power supply pins. We have 2 input pins, and we have a single output pin. So the terminology on these is that we have a voltage, VP and VN. VP is the voltage on the what we call the non-inverting input, and we call it non-inverting because it's the one that is labeled with the plus sign in the op-amp symbol. So this one is the non-inverting input, and the N is the voltage on the inverting input. Inverting input is the one which has the negative sign. So this one here is the inverting input. There's a positive and a negative supply rail. So we will often use a symbol VCC here to indicate the voltage, which is the kind of supply for our entire circuit. And op-amps often use also a negative voltage, which would usually be the same, so symmetric. So we have plus and minus VCC. So VCC is the power supply voltage. If you hook the op-amp up like this, where you have plus and minus VCC, then that's said to be dual supply rails. So if we have plus VCC and minus VCC, then this is called dual supply rails. You sometimes have op-amp circuits where you have only a single supply and your negative power is ground, but often you use a positive and negative. So that's kind of the most common scenario, and that's where we're going to start in our analysis. And then the output, we call VO for output, and that's the final pin, which is kind of on the right-hand side here. So the overall circuit symbol is this triangle. Sometimes the power supply symbols are not drawn. So sometimes we leave off the power rails, in which case we would draw just the triangle shape. Now, of course, in real life, your circuit has to have a power supply. So this is sort of just a shorthand terminology. So you sometimes see people draw op-amps like this, and then it would be documented elsewhere what would be the actual supply rails for your circuit. So if you have a design which has many op-amps, you might kind of leave off those power supply rails because they're the same for everything. But you still need to know what they are, and you still need to connect them. It's not going to work without the power supply connected. Now, the way that an op-amp works, if I write, let's just label these again, VP, VN, and Vout. So the op-amp produces an output voltage given by Vout is equal to some gain constant, which depends on the model of op-amp that you have, multiplied by the difference in the input voltages. So VP minus VN. So it produces this voltage which is proportional to the difference in the input voltages. proportional to the difference in the input voltages. So that's kind of the key point of how an op-amp actually works. Now, in reality, when you have actual power supply rails, and you might imagine this output voltage obviously can't grow without limit, so a more realistic depiction must also consider the power supply. So if I was to draw a graph of the output voltage, so VO for output, as a function of the difference in the input terminals, so what I'm plotting here is Vp minus Vn, then there will be some region where there's this linear function that we previously talked about, and that will be around 0. So it will be a linear regime like this. But as soon as the output voltage reaches the power supply, all right, the op-amp is not able to just generate a higher voltage than what you give it. So there will be some clipping of the input voltage. So in this diagram here, we have a linear regime, and we have a saturated regime. And the point at which we have this saturation, so the value over here is positive VCC, and the value down here is negative VCC. So VCC is our power supply voltage. So this op-amp will be linear within this range, but it can't just magically produce higher voltages. They actually will saturate when you reach the limits of the power supply. Now this is kind of an idealized description. You know, a real op-amp is not perfectly linear, and it's probably not a perfectly sharp corner at the top, but this is a good enough description that we can actually make a lot of progress in understanding the behavior of op-amps. Another way that you could think of their kind of internal dynamics would be as follows. So you could imagine that if I draw a really big picture, so the internals of an op-amp can be approximated as that I have this device which has these kind of input terminals, and there's going to be some resistance between them, which will be really large, but there'll be some resistance between them, large because we don't want very much current to flow into these terminals in a good op-amp design. But the thing that's connected to our output here is going to be basically this voltage-controlled voltage source. You can think of it like this voltage-controlled voltage source, which is our gain times Vp minus Vn, where Vp and Vn are the pins at our input here. And so this kind of structure is sort of what's happening inside of the op-amp. So you think of it as a voltage-controlled voltage source, where it depends upon the difference of the voltages at the input. So that's kind of the high-level overview of what op-amps are actually doing. So as a quick recap, the most important things for you to remember. So you have to recognize this circuit symbol and be able to draw it, and you have to know this terminology. So we have a non-inverting input and an inverting input, and you need to know which is which. And then the behavior of this op-amp is basically to produce this linearly amplified voltage which depends upon the difference between the two pins. So the output voltage from the op amp is 0 if the two pins are equal. So that's the kind of origin point here. Vp equals Vn, output voltage will be 0.